Hello all, welcome to video 2 of section 1.4. Right, so recall, if we're given an equation of this form, a vector equation, x1 times a1 all the way up to xn times an is equal to b, we know that this vector equation has a solution, or yeah, if it does, then b is a linear combination of the vectors a1, a2 up to an. That's just what linear combination means. It means that we can write b as some yeah, real number times vector plus real number times vector all the way up to RANs. Okay, and so yet another way of saying that is that B is in the span of the vectors A1, A2 up through AN. Okay, and if you need to go back and check those definitions, I absolutely encourage you to do so. There's lots of definitions we're working through this first little bit. Maybe like an upshot to tie this into the previous video is that the matrix equation, AX is equal to B, this has a solution if and only if B is in, B. The vector is in the span of the columns of the matrix A. Span of the column vectors of A. All right, and as always, we'll do some examples to make this more concrete. So given a matrix A and some sort of arbitrary vector B, we might reasonably ask, does the matrix equation AX is equal to B have a solution no matter how we choose B? And this depends entirely on what our matrix A is, but certainly we can try and row reduce with a vector that looks like B1, B2, B3 and see what happens. All right, so let's get the augmented matrix up here and start row reducing. So our augmented matrix looks like what? 1, 1, 2, B1, 2, 0, 2, 0, 6, B2, 3, 4, negative 1, B3. Yeah, and what should we do here? Give ourselves some space. Well, yeah, we can do the thing we always do, which is try and clear off. Yeah, we can take this to be our pivot, our 1 up in the top left corner, and try and kill off the 2 and the 3 here. So we'll do what? Row 2 minus 2 row 1. We'll do row 3, minus 3 row 1. So our row 1 isn't going to change at all. Our row 2, what's happening? We've got 2 minus 2 times 1 is 0. 0 minus 2 times 1 is negative 2. 6 minus 2 times 2 is 2. And then we've got now B2 minus 2 times B1. So this just becomes B2 minus 2B1. And similarly, what's happening downstairs, we're going to get 0, 1, negative 7, and B3 minus 3B1. Okay, and the question is still, does is there a value for this vector x that makes this thing true? Okay, so we're still trying to figure out if the system is consistent or not. Is really the only question we're asking. So let's see what we can do here. Yeah, we can take this down to be a pivot and try and destroy the 1 beneath it. So we'll do what? R3 plus a half of row 2. So our row 1 stays the same. Our row 2 isn't changing yet. And our row 3 is what? We've got 1 plus a half times negative 2. So that's 0, of course. We've got negative 7 plus a half times 2 is negative 7 plus 1 is negative 6. And now this is going to be a mess, but that's life. We've got B3 plus a half times this thing. So it should be, sorry, we would row 3 plus a half times row 2. So we've got our B3 minus 3B1, and then plus a half of what we had upstairs there. So a half of B2 minus 2B1. So what a mess, but that's life. And I think actually that's as far as we need to get. We've got pivots. We've got 3 pivots. There's no way. So yeah, the important thing to notice is that yeah, our system has no row of the form, trying to write really quickly, it's not working for me, no row of the form all zeros and then something non-zero in the last column. Has no rows of this form. And so that means it's consistent, right? The only way we get no solution is if we have zeros being is equal to 1 or something. So this means our system is consistent. And this follows from theorem like 2 back in section 1.2. Yeah. If it's consistent, it means it has some solution. Has a solution. Which is actually kind of cool because it means we actually showed that this equation has a solution no matter which B we choose, which is not always going to be the case. And in fact, if you want to see an example where that isn't always true, yeah, so you can, yeah, for an example where this doesn't hold, where this no longer holds, see what? Example 3 in section 1.4 of the text. Or you could also check if our matrix A is different. 1, 1, 2, 2, 0, 6, 3, 4, 5. So I think we changed the 5. Yeah, instead of 3, 4, -1, it's 3, 4, 5. If we change the -1 to a 5, all of a sudden it's not true for every B. We need to choose our B slightly carefully to make this for there to be a solution. So if we check, if we change our A, yeah, we no longer get a solution. Yeah, then AX is equal to B, not always consistent. Okay. Good. And so yeah, theorem 4 here, which is peeking its head out, is giving us some sort of summary of the relationships between pivots and consistency and our matrix equation. Okay, so let's take a look at what this theorem says. So let A be an m by n matrix. The following statements are equivalent. So that means we're going to give you 4 statements. Either they're all true for a given matrix or they're all false. You can't sort of pick and choose. If one of them is true, they all have to be true. If one of them is false, they all have to be false. So yeah, so what's a good statement we could start with? Yeah, so for each vector B in Rm, the matrix equation AX is equal to B has a solution. Has a solution X in Rn. Okay, so we're gonna write down 3 other equivalent statements to the statement. So B is each vector B in Rm is a linear combination of the columns of A. Linear combination of the columns of A. Okay, so we're, yeah. Statement C is that the columns of A span Rm. And then finally, A has a pivot position in each row. Pivot position in each row. Okay, so the claim is these are all equivalent statements. If you're interested in whether or not A always has a solution in the equation AX plus B, you might start looking for pivots of A, for example. Or if you're interested in whether or not A spans Rm, you might try and solve the columns of A span Rm, you might try and solve this equation for an arbitrary B and see what happens. So they all give information about each other. Okay, and you might also reasonably ask, David, I'm unconvinced that these are all equivalent. Why should I believe you? And that's always a legitimate question. And my answer is I'm going to punt. I'm going to say the textbook has a great explanation. I encourage you all to first to think about it yourself and see if you can't say why, assuming A, we should be able to see that C is true or D is true. But if you get tired of that, the textbook has a great explanation. So in an effort to keep these videos concise, I'll leave it to you to check out the textbook. Okay, take care, everybody. I'll see you at the next video.